Okay.
Dear colleagues, good morning, everyone. It's my great pleasure to continue our international workshop, Quantum Research and Education in Europe and in Ukraine, session number 3. I'm the moderator, the chairman of the session. My name is Sergei Shevchenko. I am from Institute for Low Temperature Physics in Kharkov. And I would like to give the floor to the first speaker, Volodymyr Tkachuk from Ivan Franko National University of Lviv. Please, Volodymyr.
Thank you very much. Good morning. For me, it is a great pleasure to be here with talk. And first of all, I would like to thank organizers and especially Professor Tkachuk for invitation our group, quantum group for presentation of a result, not only research result, but also teaching of students. But here I present mostly, I will be focused on just our research result, a recent result on quantum computing. The subject of talk is study of properties of physical system on quantum computers. But more details of this subject or detailized is just spin energy detection on quantum computer. It will be an example of study of properties of physical system on a quantum computer. And I would like to stress also that this result which I present here, it is result which we obtain on IBM quantum computer. It is a real quantum computer, not simulator. We have access by internet to these computers, and the result which we present here is just exactly a result obtained on quantum computer. Here is a collaborator of these results. It is Christina Hnatenko from our department for theoretical physics, and Hanna Laba, it is Polytechnic University. The main points of our talk, my talk is here. First of all, we consider, maybe first of all, I say the main idea of calculation energy levels using quantum computers. Of course, we cannot directly find energy levels, but we can, without some problem, but not very problem, to find evolution of some mean values, some physical quantity on using quantum computer. So as a result, we have time dependence of this mean value. And you understand that this time dependence depends on frequencies or maybe energy levels of quantum system. So idea is to find, using evolution of mean value, to find energy level. This is main idea of this research. So then we consider just evolution of some mean value, find time dependence of this evolution of quantum computer. Then this method, which I propose here, we generalize to more generalize this method, which we call as probe spin method, and conclusions. I understand that it is difficult to find what is idea mean from the start, but let us consider next slide. I hope it will be possibility for me to explain what I mean in this talk. So first of all, this very simple, in fact, idea. Let us consider evolution of wave function or state vector. Evolution can be presented in this form, where E is just eigenvalues of Hamiltonian. starting from arbitrary initial state, evolution of this state can be written as here. So then let's consider some physical quantity to which we correspond some operator A. So then mean value you can calculate without problem, and result can be written here. You find that mean value depends on transition energy, transition between energy levels, and omega here, it is just frequency which corresponds to these energy levels, transition between energy levels to energy levels. So starting of some mean value, we can find time dependence, and this time dependence contains frequencies, difference between, which is related with differences between energy levels. Then when we consider Fourier transformation of this time dependence, you find that Fourier transformation have sharp peaks just at these frequencies. So from this just peak, you can identify, you can find translation between energy levels using this result. So idea is the following: when you want to find transition between energy levels, you can find on quantum computer time dependence on mean value. Then you use traditional classical Fourier transformation, and from the peak you find result which you want. So this idea, this algorithm can be considered as mixed quantum computation, because here we use some calculation on quantum computer, just exactly time dependence we find on quantum computer. But next step is just classical calculation. It's classical calculation on classical computer, where we use Fourier transformation. Therefore, it is mixed algorithm which use quantum computer and classical one. So this is main idea of this research, but you find here that using this proposed algorithm, you can find not energy levels, but difference between energy levels. It is not very good because, for instance, when you have n energy levels, so you have approximately n squared energy levels. More exactly, n multiplied by n minus 1 divided by 2. It is n squared. Of course, it will be better to find directly energy level. How we can generalize this method to find not difference between energy levels, but exactly energy levels. And the idea is the following. Let me omit this explanation. It's not very important, but important is just this slide. So we want to find just exactly energy levels of quantum system. So suppose that we find some operator A, which anti-commutes with Hamiltonian. It's written here, this is anti-commutator. So A and H anti-commutes. So then you can find that then energy spectrum possess very simple properties, namely that energy spectrum of such system is symmetric with respect to inversion of energy. It is important properties of energy level of such Hamiltonian, for which exist operator which anti-commute with this Hamiltonian. Okay. And what is interesting, in this case, you can find also supersymmetric algebra, which corresponds corresponds just exactly to these properties of Hamiltonian, just exactly to the properties of symmetric energy spectrum with respect to inversion. I also need this interesting relation, who are interested can be considered in more detail this point of my talk, but I omit the details of this explanation. So then let us consider evolution of this anti-commuting operator in evolution in time. What is important? Important that A anti-commutes with Hamiltonian. Then, using these anti-commuting properties of operator A, you can rewrite mean value in this form. And here you obtain exactly exponent or operator of evolution with Hamiltonian, but multiply it by 2. And we can easily calculate a mean value. This mean value using eigenvalue of operator, eigenvalues of, or maybe not eigenvalues, eigenstatus of Hamiltonian, because this psi 0, it is initial state which can be developed using eigenstates of Hamiltonian. As a result, you find that operator or mean value of operator depends exactly on energy levels. Here we find that this dependence contains omega, and this omega is just exactly corresponds to energy level, to J energy level. So it is very important for us because using this result and calculating mean value of some physical quantity on quantum computer, you find that this time dependence contains exactly energy levels of system, not difference between energy levels, but exactly energy levels. So we, of course, then we use Fourier transformation, and you find that this Fourier transformation have a sharp peaks at point related with energy level, more exactly double energy levels, but it's easy recalculate. So its main idea of this method is you have some Hamiltonian, you find operator which anti-commute with this Hamiltonian, then you find a quantum computer. You find quantum computer time dependence of this physical quantity. Then you use classical Fourier transformation and you find energy levels. Let me start from very simple, simple system, more simple which we can consider. Most of them, it is spin in the magnetic field. We consider one spin in magnetic field directed along z-axis, Hamiltonian is here, and you find that easy calculation, it's analytical calculation, trivial, I would like to say, that frequency, that mean value depends, Fourier transformation of time dependence of mean value have 2 peaks, which corresponds to energy levels of this Hamiltonian. Here is presented a protocol, quantum protocol for calculation of mean value. I would like to say that for calculation of mean value of corresponding spin, but I forget to show you here that for this Hamiltonian, you can easily find operator which anti-commute with Hamiltonian. It is Pauli operator or Pauli matrix, X component of this Pauli matrix, because here you have Z component, X component anti-commutes with Z component. So operator A, which anti-commute here is X component of Pauli operators. And here, very important point of this protocol is this operator H. This operator prepare initial state. In this method is also important initial state which we considered. And this operator, it is Hadamard operator, which prepare state, such state which contain all possible eigenstatus of Hamiltonian. It is not Hamiltonian, it is Hadamard operator. Here it is just operator which related with evolution operator and measurement. Measurement is also, of course, important in this method. Let me omit how we measure it, but computer which we use here, it is real quantum computer, Manila quantum computer, IBM's company, IBM computers. And a row corresponds to a relation between these qubits, direct relation between qubits. But for this system, it is enough only one qubit. I would like to stress this. You have spin in magnetic field. And in order to find evolution of this spin, you need only one qubit because we have absolutely direct relation between quantum bits and spins. Here we have mapping, exact mapping between mapping of spin on the qubit and qubit on spin. So in order to find evolution of one spin, you need only one qubit. Here is presented result for mean value of this operator, X Pauli operator. Red line, it is analytical calculation, and this it is result obtained at quantum computer. Here is Fourier transformation, classical Fourier transformation using these crosses. Of course, here we use discrete Fourier transformation because we have a result obtained in some discrete times. So we find here two peaks which just correspond exactly to energy levels. And very nice picture, result which obtained from real quantum computer. But it is only one qubit. What we get in more complicated system, it is system which contains three spins, 0, 1, and 2. Here we can also find operator which anti-commutes, also X operator of Pauli 1. You can easily find that the operator anti-commutes Hamiltonian. More complicated quantum protocol, quantum algorithms for calculation. His result not so good as in previous case, but nevertheless, let us look what we get using Fourier transformation. Result is also very nice. And you find here three peaks, which just exactly corresponds to energy levels of this system. More complicated system. Here we consider 4 spins on square lattice, on square. Here we also can find operator which anti-commute written here. And more complicated protocol, 4 spins, results not so good. You find here we consider different Hamiltonian with the same constant of interaction between different neighbor spins, and here some sign is different. So two different Hamiltonian, and result is presented here. For first Hamiltonian, for second, result not so good as in previous case, but nevertheless, let us consider Fourier transformation. You find that these peaks exactly corresponds to energy levels. It is strange for the first time when we find this result. It was very strange for us because result for time dependence is not so good, but peaks absolutely very good corresponds in a very good way corresponds to energy levels of system. And once more example, more complicated and computer which we use, we have many quantum bits, but for us, very important is only these six bits. And we consider interaction of spins pointed at 0, 1, 2, and so on. So we have 6 spins with such Hamiltonian. And in this case, you can also find operator which anti-commute. What we find here, protocol is more complicated, time dependence. When we look at this result for the first time, we think that it is impossible to get energy levels because this analytical result, you find it is a red line. And blue, it is just exactly a result obtained with quantum computer. Seems it impossible from this result to find something, to find energy levels, but nevertheless, we try to find Fourier transformation. What we find? We find Fourier transformation, and result for real quantum computer is presented here is not so good, but nevertheless, let us compare this result with result obtained with quantum simulator. Just exactly, we have peaks corresponding to energy levels, but you can find that real quantum computer also give peaks at points which we get on the simulator. These two peaks, this one, also this one. So result not so bad. Of course, not so good, but we can understand that quantum computer which we have now is very noisy quantum computers. But nevertheless, this method, even in the case of 6 spins, and in the case when time dependence is not so good, Fourier transformation gives some not bad result for energy levels. Okay, and finally, I would like to consider generalization. I understand the time is over. What we can do in the case when Hamiltonian does not possess symmetric properties of energy spectrum. In this case, we can generalize proposed method using so-called Antilla spin or probe spin Antilla qubit. We can generalize this Hamiltonian to more complicated. We multiply on some operator, and just this Hamiltonian possess necessary and energy spectrum. Here you can easily find also operator with anti-commute with this total Hamiltonian. We call it as a total Hamiltonian. And for this total Hamiltonian, you can apply method which we proposed previously. So I omit all this explanation. Also, we can find the properties, supersymmetric properties of this total Hamiltonian. This fact is also very interesting from theoretical point of view. But from practical point of view, it is necessary that we can find operator which anti-commutes with Hamiltonian. Here is protocol general protocol for calculation. Also, here is important to prepare initial state, which contains all all states of total Hamiltonian. And here are some results for very simple example for this generalized method. Let me omit, but I show only you the result for Fourier transformation. And these peaks also corresponds to energy level. More complicated Hamiltonian, for which we cannot find directly operator which anti-commute, but we can use a more general Hamiltonian, for which we can find operator anti-commute in this total Hamiltonian. And the result is presented here. Also very, very good result. These peaks corresponds to energy levels. I omit this example because I understand that time is over and conclusions. Finally, I would like to show also a publication where you can find details of proposed method, very recent publication. So it is here, and thank you very much.
Thank you very much, Volodymyr, for the very nice talk. You have a unique experience in Ukraine of calculations on quantum computers, on real ones from IBM. Now the talk is open for questions.
Thank you.
Yes, Alexander Kardyuk, please.
Okay. So the question is the following. Let's say I have just several questions. So, for example, let's start from this three comparison of one qubit and three qubits, right? Okay. So you have some first why it is so more general naive question, why it is strange. My understanding is that I understood that you put by hand the parameter of this energy, so the frequency, and then your system oscillates and you get this frequency back. So it shows that it works, right? But when you have three qubits, so first they interact with each other, and this actually what you get some constant component, and constant component. So the question, what is the origin of this constant component, you think? And then it is I think it's not strange that the constant component give you just central peak and two let's say frequencies, right?
Yes, of course. So let us start from this more simple example. Here you have omega 0. It is arbitrary constant. It is arbitrary constant, and when we consider evolution of some operator on quantum computer, of course, I cannot write omega 0 on quantum computer. I put, instead of omega 0, some constant, for instance, 1, 2, or 3. This depends what you want. So quantum computer does not know what I put. Maybe I say in such a way. I consider evolution of this Hamiltonian with some constant, for instance, 1, 2, or 3. You don't know what I get here. And then I ask you, okay, using this method, try to find what I put here instead of omega 0. And using method which I propose, which our group propose, you find that omega 0 corresponds to 1, which you put by hand. Of course, it is correctly, you said correctly that I put here in Hamiltonian instead of some parameter, some concrete value. And then using method on quantum computer, we find this concrete value. More complicated, of course, here for 3-spin where it is, because here we have some parameter interaction,
yeah,
of course. And here we by hand put here some value, but energy level does not correspond exactly to this.
But then should be you should see splitting of
yes,
energy levels, right?
Find some energy level you find here. So energy level is here. It is 0. Of course, these energy levels or frequency corresponding to energy levels is related with this interaction, which you put in Hamiltonian by hand. But on quantum computer, you find exactly energy levels. Of course, when you have some concrete system, instead of interaction, you must put some value.
So maybe the question better to ask why you don't see the splitting, you think, but you see this central peak, which just corresponds to constant component.
This peak corresponds to energy levels of system. This energy level corresponding to system. Look here.
But energy level corresponds to frequencies, and central peak, it corresponds to 0 frequency.
Central peak, yes, corresponds to 0 frequency. And this system with 3 spins also possess energy levels with 0. You can very easily find energy level of this system. You find that energy level of this system. It's a very simple system. In order to find energy level, you must put instead of sigma 0, sigma 1, and sigma 2 value plus or minus 1. And then you find all possible energy levels. And energy levels is here. It is 0, one of the possible energy level. and you have also two energy levels.
Okay, I understood. I just missed the point. I didn't understand where I initially. So for one qubit, it is its frequency, yeah, and its frequency it is its energy. And now this means that this energy is zero energy, and you have just split in plus and minus, and there is no omega zero frequency here.
Omega zero is here.
Okay, omega zero is zero here. Okay.
Yes, and
so I didn't understand how it's just.
This omega zero corresponds to energy levels.
But for one qubit, omega zero shows two peaks.
Omega zero, okay, omega zero.
Oh, it is for one qubit. For one qubit,
omega zero, it is not the same omega zero. It is different Hamiltonians.
Okay.
Zero here.
Omega zero is not the same as omega equal to zero.
Yes, zero is not the same as omega equal to zero. Here you can put also, instead of h omega zero, you can put another constant.
I mean that here omega zero is first harmonic, and this is only harmonic, finally. But then, okay, I no.
Yes, of course. Here you can only you have only one parameter, but here you have two energy levels, plus minus omega zero.
Yes.
Two energy level.
Yes.
Of course, one harmonic because plus minus, but you have two energy levels, plus minus omega zero. You can find here that you have symmetric just peaks, which corresponds to plus minus omega zero.
I mean that I would expect that if you add interaction J, then you have splitting of each energy level. So about each energy level, but not such as three peaks. But okay, I understood that. I do not understand this.
In fact,
how you transfer one.
It is Eisenhamiltonian, and here you can easily calculate energy levels. In fact, put instead of sigma 0, sigma 1, and sigma 2 value plus minus 1, you find all energy levels. So it is spin Hamiltonian, there's no problem. Of course, when we consider a more complicated Hamiltonian, for instance, Heisenberg Hamiltonian, you cannot find in such simple way energy levels. It is a complicated problem. You can find analytically too. Also, you can find energy levels, but in a complicated way. But here it is no problem. And splitting, when you speak about splitting, what it means? It means that you have some Hamiltonian when energy level is degenerated, and then you include some interaction, which leads to splitting.
Yeah.
But here, it is not such situation. We have such Hamiltonian, and okay, let us find energy levels. You find just energy levels.
So it is exactly difference between classical system and quantum systems. Yeah, one could say.
Yes, of course. You can consider this Hamiltonian. It is very important notation.
Dear colleagues, I'm sorry, I must interrupt you. We are somewhat behind the schedule. Of course, the discussion is very interesting. The talk is impressive, and I saw that there are more questions. Sorry, but we need to continue so that
let me finally only show this result, which I omit.
Yes, very quickly, please.
It is just exactly a quantum system because two terms does not commute, and in this case, method also work. I presented here, but not show you because of time. So sorry for time is over. Thank you very much.
Thank you. It's my great pleasure to invite next speaker, Pavel Gora, from University of Warsaw in Poland. Volodymyr, please unshare, stop sharing